Okay, um, welcome back. That was kind of an awkward spot to take a break because I'm just about done this slide deck. But anyway, um, so neural networks, deep learning, the gradient descent algorithm, these are all super interesting and super cool. They're kind of not what this course is about, but some links just in case you're into it. I think, you know, as a data science technique, neural networks are often overkill because, again, like most data sets aren't that big. The decision that you're making is not that complex, but they're a good tool to have in your pocket. I keep saying deep learning. I hear myself saying it. Deep learning is basically all of that, but even more. If you have a neural network and it's kind of a really big neural network with a lot of layers, okay, deep learning. And I think one of the things about neural networks is, I guess you have this really obvious way to dial up the complexity of the model, right? It's like more hidden layers, bigger hidden layers. You can tune the way things are connected in those hidden layers. You've got a lot of dials to turn and a lot of, especially, ways to turn up the complexity. Okay, great. If you have a lot of data and a big neural network, fine. You know, like back this relatively ancient example, like 2014 is now the distant past. But this is, so each one of the boxes here is not a node as I've drawn it, it's a layer as I drew it in the previous visualizations. 7 million or so parameters. Well, okay, you're going to need a bunch of computation and a bunch of data, like training data, to sort all that out. This is right, it's right there. This is a computer vision problem. So this is image comes in and the output is that's a cat. Okay, you know, great. Different course, different size problem. Andrew Ng, which, you know, by any measure is a data science expert. It's a 10-year-old quote. So 10 years ago, this was his estimation of what could be done. You know, if a human brain can do it in less than a second, it can be done with AI 10 years ago. I kind of like, if nothing else, I kind of like this, like, human thought seconds as a measurement of the AI quality. Anyway, let's wait, was that that was the last slide there, right? Yeah. Let's move on. So what I just talked about there was all classification. And, you know, classification's fine and all. We've certainly been in the supervised learning category all the way through. And this is where basically, if there's training data, right? If you have training data and you're trying to train a model that that produces output like the known examples in your training data, you're doing supervised machine learning. Unsupervised learning, I'll talk about, I think a few examples will make it as clear as anything. You know, I think it's hard to look at the definition of unsupervised learning and understand what that could possibly mean. I want to drive this distinction home a little bit. What we've been doing in that last slide deck were all classification problems where the target, the thing you're looking for, is a discrete class. Regression, which I did talk about early on, I said, oh, you know, you can think of linear regression as a machine learning technique, and then it's a numeric prediction where, I guess, close is close, right? So if I'm predicting categories, if I have category 1, 2, 3, 4, 5, well, if 2 is correct and I predict 3, I am not close, I'm wrong. If I'm making a numeric prediction and you know, the numbers range from 0 to 1,000 and I predict 200, but 201 was correct, I'm happy, that's really close. So that's a distinction here. And I'm not going to talk a lot about regression because it turns out I already talked a lot about regression. You just have to make the techniques we've talked about in the last slide deck into regressors. So, like, I have I have over here, I created some data, right? Like, again, some fake data for a slide. What the heck? So you could do linear regression on that. Okay. So I've done this as if it's a machine learning problem, right? I have done the test train split. I've trained the model, a linear regressor, on the training data. I have plotted the result. Okay, fine. Okay, well, I guess I'm plotting only the validation data here. If you're going to put a line across that data, sure, but that's not linear data. Like, it's not a linear relationship. So what do we do? Like I said, it turns out the classifiers that we've been using, if you just sort of take exactly the same technique and just at the last moment change how the prediction works, you have a regressor. So I'm going to talk less about regression than I did about classification, not because it's less important, but because we already know about it. You just have to sort of, change the score, certainly. So the accuracy score that we were using for classification, basically coefficient of determination is that thing. It's basically the R-squared value. And well, it's still between 0 and 1 is still good. So that's super handy, right? I can still look at my score with the exact same thought. 1 is good, 0 is bad. And well, let's look at k-nearest neighbors, the regression version. So in the classification version, what we did was say, okay, well, we'll have our nearest training points and vote whichever category is most represented in those k-nearest training points. That will be the output of the model. Now, instead of just voting, well, it's actually even easier. Maybe we'll just take the mean. So I find the 5 closest training points to the input, average those. Well, now I have a numeric output, so I'm doing a regression, and it turns out that works pretty well. So like for this data set, so this is like linear, and then I have like one full cycle of a sine curve in there. That does pretty well. I don't know that I want to do all of these as an example. I think, at some point you would take my word for it that I'm not totally lying on the slides, but why not? So I guess you maybe see a little bit of the limitation here, right? Like inherently, this is going to be kind of a stair-step output because it's, well, for as long as the 5 training points are the same 5, the output will be the same. Maybe 5 is not the right number for this data. Maybe 7. No, it probably doesn't matter very much. That's not bad. Now, again, data limitations show themselves, right? Like I don't have presumably any validation points over here. That just happens to be the couple data points over there got pushed into the validation, not the training data. Okay, so I'm kind of undertrained off on this very left-hand side of my world. But otherwise, it seems pretty reasonable. I get to dial a k up and down again with the same thing, right? Larger k's takes more evidence to move the output, but I might be less likely to overfit. For random trees and random forests, same thing is happening. Again, I'm choosing the random forest regressor, not the random forest classifier. That is an important distinction. That's really easy to miss just because, your fingers do the wrong thing as you're typing. So, and this is really easy, right? This is just instead of, on the leaf of my decision tree, putting a category, put the number there. And then I guess if I have a bunch of random forests, I will make a prediction with each one of them and average them. Yeah, that seems totally plausible. That seems like it should make some results, right? And yeah, it does. And once again, I'm limited by the complexity of my model and my training data. Maybe I need a different thing here, right? Like this is different data than I had in the slides, so maybe different parameters would help. I'm gonna call that a win, I think, and move on. I could spend a little bit more time on this. Obviously, there's more parameters to hyperparameters to play with for a random forest, but again, the difference is just change a little bit what you do on the leaf, and instead of a vote, take an average, and all of a sudden your ensemble of trees becomes a regressor instead of a classifier. Same thing, I guess, for boosted trees. Same kind of thing can happen. So cool. A neural network, same thing. So the story that I told on the neural network was on the output layer, have one node for each category and then use softmax to turn it into a probability and choose the highest one. Well, now if what I'm doing is regression, well, just have one thing in my last layer and don't do anything to it. Just add them up. Okay, and then take that number that comes out, and that's a number. Okay, I'm now predicting a numeric value, and I'm doing regression. Okay, yep. There we go. What happened there? What do you mean it's not? What fat fingered thing did I just do there? Input variables, inconsistent number of samples. That comes as a surprise. What? There's only one input variable. Oh, wait, how did I must have hit undo on that slide. Okay. Okay. So I get a warning here. And the warning is something like that the training process hadn't converged. Within some limit on the last iterations of the backpropagation algorithm, that we're still changing these weights. This seems like maybe either you need to train for longer or you need more data. I'm going to ignore that warning, and okay, that's that. I guess because of that logistic activation function in the middle, I can do nonlinear things here, even though I'm sort of thinking about weights and linear combinations. Having that activation function be nonlinear lets me have a nonlinear output, and this feels good. Maybe I should compare. Oh geez, I didn't even print the training score. I just totally YOLO'd that one. Training score, validation score. I'm not going to bother going back through. Okay, like I don't feel like I'm overfitting there. This should worry me. It's not going to worry me right now. I could think, hey, I got some freedom here. I can make a bigger, more complex model and get a worse score. Probably now because I am overfitting. Probably. Or again, it could be overfitting. It could be I don't have enough data to train. So effectively the models, the weights in that model are still a little bit random by the time this training is done. I don't really know which is which, and you know what? It's going to have to remain a mystery for the demo. So again, the difference is just what do we do on the last layer? Fine. That looks good. I only have one input feature here, right? Like I'm not doing a very complex thing because, well, I have one input feature that I can plot on the x-axis, and I've got to plot my output. It's now numeric, so it's not going to be just a color. It's going to be on the y-axis. I could do a more complex thing here. For the purpose of the demo, I'm going to live with it. So remember, these are out there. If you choose a regressor when you need a classifier or vice versa, things are going to get weird and ugly, and you're going to have a score that is meaningless. But well, you can predict a number just fine. And again, like we basically didn't learn anything. We didn't do anything new there. That's the techniques we saw in the last slide deck. Just change the very last thing that comes out so that you get a number instead of a category. Okay. I promised unsupervised. So again, all of those were supervised machine learning because there's training data where we know a correct output. Here, clustering is an unsupervised problem. And that's just, I want to find similar data points. I don't know what it means to be similar. I don't know what my categories are. Like effectively, I'm generating like I'm categorizing my data here in ways that make things similar. And here's my story and my demo. I have 5 categories here that are just random generated: red, black, green, yellow, blue, and okay, fine, right? Like definitely, red and black are up there, but I pretend I don't know that, right? So I have data like this, and what I think is I would like to take my data points and somehow put them into different categories. So this could be something like I have customers from my online store, and the customers have different properties. They have how many purchases they make in a month and how big those purchases are and whether or not they call the sales rep and whether or not they make returns and whatever features I can imagine for like my online store. And I want to take my customers and I want to somehow figure out who they are. Like, are there categories of people that behave differently? Like probably there's people, or there's like normal behavior that most of my customers do, where it's like, they order once or twice a month and it's $100 or whatever. But maybe there's a different category of users who order 10 times a month for many, many thousands of dollars. I would like to know. I would like to know if that category is out there, and I don't know, again, assign them a sales rep or whatever it is you do. So it's basically, I have, again, this picture that I'm imagining that's like, okay, how many orders per month and how much whatever. I want to categorize the customers, and then I can kind of look at it manually and try to sort out, like, who are these people that are all behaving the same? Or maybe there's people that return a lot of things and they're actually trying to do fraud, whatever. Hopefully I can discover that. I guess as I say that, clustering is a data exploration tool, right? It's something you can do to sort of have a look at your data and try to just figure out what's going on in there. So k-means clustering here, this is like the only thing I'm telling it is how many clusters. I bet there's some other things I could tell it. For example, what does it mean to be close? I bet there's some kind of metric. Oh, maybe not. Maybe it is straight Euclidean distance. But hey, this is pretty good, right? Like if I had these data points, and again, the input is effectively this. I'm just saying, hey, here are some data points with X and Y input values. Tell me if they can be categorized somehow. And the model decided, okay, we've got these 5, and it doesn't matter that the colors don't match, right? It's I have a category. It happened to be colored black in the output here, but it doesn't matter. That's pretty good, right? Like if I gave you this data and I said, okay, there's 5 categories of thing here, break this data up into 5 categories where things within that category are kind of similar. Okay, like 1, 2. It does pretty well. And of course I can choose, like I chose 5 because it matched my inputs that I thought I would try to see if I could match the, the inputs to the model, but I could have chosen a different number there. I could have chosen 3, I could have chosen 15. And I think this is pretty good. And if these are customers on the website, I can now say, okay, well, the category blue here, who are these people? Can I figure out something about them? Can I, give a name to that category in my head and say, okay, these are the power users or whatever. These are the ones who return so much that I think there maybe should be handed to the fraud department or whatever. So, okay, that's k-means clustering. I guess maybe a quick, couple sentences. K-means clustering. Randomly assign 5, well, K, I suppose. K cluster centers. Just say, okay, well, there's going to be a cluster here, 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 and here. 5 of them. And then the sort of calculation is, okay, take each data point and assign it to the cluster center that is closest. Now we have a cluster. Take the data points and average them. That's the new cluster center, and repeat. So just kind of move the cluster centers around until they're nicely kind of representative. So there is some cluster center in this model. It says, okay, if the center of black is here, the center of yellow is there. Agglomerative clustering. I get to choose my number again. And this is, I believe, this is like, okay, how many clusters I have for every data point is its own cluster. And then start taking two clusters that are kind of similar to each other and joining them. Keep doing that until you're down to 5, I think. Pretty sure that's agglomerative clustering. Wherever you are right now, try to say the word agglomerative out loud. You think it's easy, then you give a lecture, and then you can't say it. Anyway. Affinity propagation is, I guess, kind of nice. And like, I didn't say anything here, even random. I don't know why I put random state there. That is the default. So even with no parameters whatsoever, it chose these 6 categories. Okay, that's cool. I didn't know that 6 was the right number here, maybe in this story. There's some things I can do to sort of guide it. You know, how many categories should I end up with, or how similar to things have to be before they end up in the same category. Cool, right? Like, these might be tools that are worthwhile. DBScan is doing 2 things. It's finding clusters, and it's also finding outliers, which we'll talk about in a moment. So the outliers here are red, and then the 5 clusters that it found are the other colors. That's cool. Like, that might be really handy, that to categorize things and also find the weirdos at the same time. And there's some parameters there that you can tune, you know, to end up with how many categories, how many, you know, weirdos am I going to find. That's nice. Just as a local aside, DBScan is why Martin Esther is famous, or not one of the reasons Martin Esther is famous. The one whose office is literally beside mine. So if you're like, I don't know what these parameters are doing here, ask Martin if you're curious. I played with him until my diagram looked fun. It turns out we have like just one of the absolute best in the world data mining groups, and Martin Esther being one of them. This is a cool algorithm, and where did I see it used? It'll come to me. I was exploring something or other. I remember what it was. It was in some image processing thing, the like find similar faces. There was just this footnote of like, hey, yeah, we use DBScan for that. Which makes sense, right? Like, I don't know what features go into facial recognition, but you do some feature generation, take the images, I guess find the faces, that's before this, and then take whatever things you do to turn faces into meaningful features, and then run it through DBScan. The outliers are the ones that, you know, if I have one picture of one person in the background, fine. Okay, there's one person, that's an outlier. I don't care about them. And then here's all the pictures of, you know, me, and here's all the pictures of my wife, and here's all the pictures of the nieces or whatever. That's really cool. I'm going to do a different example of clustering. Just because I saw it mentioned, and I thought, well, that looks cool. I want to try that. This is like, you know, if you're doing PNG or GIF and you don't want a full color palette, you want a smaller number of unique colors in the image. You can end up with a smaller file that way if it kind of works. So what I'm going to do here is take all the colors in the world. So I have 3 features, red, green, and blue. I'm going to decide how many colors I want in my output, and I'm going to try to cluster the colors that exist in the image into that many clusters. I'm going to do k-means, so each cluster has a center. I can look and say, okay, what's the most representative color in this cluster? That one? Okay, I'm just going to map, then each input pixel is going to get mapped to the cluster that it is in, and then take the center of that, and then recolor the pixel into that. Long story short, and I don't know, you might want to look at the original slides. I don't know how this is going to come through the YouTube compression. But I got this image. I want to knock it down to 32 colors because I chose 32. Okay. I switched k-means implementations because it turns out if you have a lot of data points, the k-means is a bit much. Mini batch k-means is basically for each iteration randomly sample that number of data points, less computation. I didn't have to wait too long to get my output. Take the image data, shove it in there. So this is for each pixel in the image, tell me what cluster it's in. So this is just like you're in cluster 0 to 31 or whatever. And then this is 2 hard fought lines of code. For each one of those cluster centers, like map each one of these to the corresponding cluster center and get the thing the right shape so it's an RGB color again. That took a while, but we got there. And I ended up with this. And yeah, this one, who knows what the YouTube video compression is going to do, but this isn't bad. Like, it's not bad. Like, I bet if I did this in Photoshop, it would be better. Like, it would be a better match to the perceptual color, yada. But this is 5 lines of code. Take all the colors in the world and cluster them for each pixel, find out what cluster it's in, map that to the actual color of that cluster, the center of that cluster, and then I've got a 32 color image that looks pretty good. And yeah, I like it. So again, the place that I saw this was in Image's facial recognition thing. It's amazing how many things, like if you think about the world the right way, hey, I'm actually, it's a clustering problem. I think for us, definitely something, again, not you, but there will be somebody in this class who definitely could take their data for the project and do some clustering and try to sort out, do some little exploratory data analysis and figure out what the heck is going on here. What are these data points? Do they come in categories? What are the categories? Something else that is also unsupervised that I kind of mentioned when talking about dbScan is anomaly detection. And this is the like find the weirdos, right? Like I have a whole bunch of data points and some of them are weird. And maybe they're weird because they're fraud. Maybe they're weird because they're people who spend thousands of dollars on my website and I love them. Maybe they're weird because they're attackers. I don't know. So again, it's data like this, obviously fake data again. And I just want to say, okay, look, I've got some normal and I got some other normals. And then I've got these weirdos in the middle. I want to find the weirdos in a like algorithmic way. I chose local outlier factor because it didn't throw an exception when I didn't fill anything in here. Don't take this as a comprehensive demo, but okay, that's cool, right? Like, we can disagree on whether or not some of these points are truly outliers, and then of course parameterize this thing to be a little less twitchy or whatever. But that's pretty good. And again, maybe what I'm realizing here are there's 20 users on my website who I need to pay very close attention to or something, or there's 20 faces that I've never seen before in my collection of faces or whatever it is. Yeah, it's never going to be perfect, right? You're going to need to parameterize this to say, okay, how many outliers do I want to find? How many do I think there are? How many can I deal with, or whatever it is? So I think maybe the more I do this course, let's put it this way, maybe I should talk more about unsupervised machine learning, because I think these are very often exploratory data analysis tools if you look at them in the context of this course. I have data, I don't know what's going on, I'm trying to figure it out. But if you do have I have this data I'm going to think of as training data, it would certainly be really nice to be able to predict this value in the cases where I don't know it. That's a supervised machine learning problem. Again, it can be a very handy thing to do on data sets and in data science. If the thing you're predicting is a number, if the thing you're predicting is a category, then you make that choice. So is machine learning good? Well, like if you have data and you apply a stats technique, you get a p-value, and the p-value is this very quantitative thing that tells you about, whether you think you're making an error or not. That's awesome. But with machine learning, I have there's a lot more techniques, right? There's just a lot more power there. I now have a much less quantitative way to decide. Like I can look at a validation score and I can think I'm happy with that validation score, but do I trust the model or not? I maybe have a much more subtle decision to make there. But machine learning does a lot, right? Like something like handwritten digit recognition, taking this image and returning that I'm in category 5 and this image that I'm returning and saying I'm in category 9, that's super cool, right? Like that's, if you had to write code for that yourself without machine learning, you're in trouble. But it's really easy with machine learning. But how confident am I, right? Like with like CrowdMark, when you write your name on the front of the exam, it does basically this, but obviously with letters and not digits. Have I ever had an exam misread and assigned the wrong student's name? I don't think so, right? Like it does like if the confidence is below some threshold, it just gives it to the TAs or I for manual intervention. But of course, somebody had to set that threshold. Somebody had to decide they trust that model. Do I trust that model? I guess. I mean, apparently. The answer is apparently, because I do use it to read your names off the front of the exam. And it's a really easy machine learning problem, it turns out. Do I trust it? Well, again, the answer is obviously yes. Anyway, this is, we're now in project time. I think that, the stats and machine learning is realistically the cutoff for things you need to care about for the project. You are welcome to use big data tools, big data techniques in the project. But now, basically, this is the moment where I am going to declare it is time to worry about the project. You need an idea for the project. We can talk about that on Fridays or in office hours if you like. I have some not well thought through project ideas here. These are just, I had an idea, I put some stuff here. Any of these might be an awesome project or fail completely. All of them are worded in such a way that they do not, describe one specific project that can be done from start to finish, because that's not the point. But have a project idea. If your project idea includes collecting data, you need to start that real soon now. Because let me tell you, my first question, hey, I'm thinking about this for the project. Do you have that data? That's going to be the first question. And if the answer is, well, I'm pretty sure I can, then the answer is get the data now. And if you can't get it, come back with a new idea. You don't want to get to, a week before the project is due and realize, uh-oh, I thought I could get that data and now I can't. Anyway, let's move on. So this is the last big chunk of the course, the big data tools. I guess those slide decks. And then there's a few like off the end here. So do we know what big data? I think like I must be a big data expert. Like, I don't know how that happened, but I'm pretty sure I must be. And I'm not really sure I know what big data is. It's less of a buzzword than it was 5 years ago, which is nice. I don't like really being in the buzzword space. For us, the big data tools that we're going to see are effectively like competitors to pandas, maybe to, things like scikit-learn and whatnot, but like the SciPy toolkit. It's basically, I want to manipulate data, but the data is too big to kind of conveniently work with. That's basically where we're going to be here. There's 4 V's of big data. This isn't bad. I think these last 2 V's, so variety, like I have different data sets. They're kind of differently structured or, a little bit less beautiful and a little bit less easy to like unify into one thing. I think that's a data science problem. I don't think that's new in the big data world. Veracity is just a way to make the word correct start with a V, yeah, you might have data correctness problems. I don't think that's new in big data either, but I think these other two are the sort of hallmarks of big data. I have a lot of data, gigabytes, terabytes of data or whatever, or I have, another gigabyte of data every day, or something like that. Like, I think big data is kind of those things. I, as a descriptivist, not a prescriptivist, when it comes to word meaning, again, I've been around the big data world for what ends up being a long time now. This is what people actually mean when they say big data. They mean, I'm annoyed by how much data I have. I've talked to people who were annoyed about how much data they had because they had to switch from Excel to R to do their data analysis. And that is annoying, right? Like, that's, I have more than, like, what, I don't know, Excel is comfortable up to what, 10,000 or so data points, and it gets weird. I don't know what the number is. And it is annoying to switch tools. I don't want to take away that person was doing big data. But I'm not going to use Excel for my data analysis, so that annoyance isn't part of my life. I think, well, as a programmer or whatever we are, this is the point where things get annoying for me. Like, if I can take my data and I can just load it into a pandas data frame and I can do whatever, fine. So a pandas data frame sits in memory. So that's probably going to be the limiting factor on it. But, like, oh boy, I sure love the way they lay this out. Okay, like, so you can just rent this from Amazon and get 1.5 terabytes of physical memory on your 192 CPU core machine. That's a lot, and they do have bigger memory things than that too. Yeah, I stand by this. I love the big data tools, and I'm familiar with them. I'm comfortable with them. But they're not. Do they solve problems I actually have very often? Not really. Very often, I can use the tools that I know even better, and process my data that way. Pandas is annoying as you start anywhere down the scale. I'll talk about that later. Or maybe I would look at the problem this way, that even if I don't have big data, well, maybe I'm optimistic, right? I think my company is going to grow. I think my data set is going to grow. I would like to be ready when the data gets bigger. Or, if I have, what was that, 1.5 terabytes? If I have a 1.1 terabyte, in-memory data set, I could technically process it on that computer, but maybe the amount of time it's going to take does not make me happy. Maybe I want more than one computer situation because I just will go faster that way. So if one computer is not enough, I guess I need more than one computer. And here we enter the world of a compute cluster. There's, of course, other ways to have more than one computer work together to do work. This is the one we're going to talk about. So we have a compute cluster for this course. Good timing for me recording this lecture. We've just decided we're not up. There's some question about the new one or the old one. We're going with the old one. The tech staff are not mad keeping the old stuff running for another month or so. We have this. There's more than 4 computers, but 4 actually doing work, 60 CPU cores, 64 CPU cores actually. A couple are held back just so the operating system doesn't starve. Okay, in the modern world, absolutely you can, well, I don't know your budget. One with a not too crazy budget can buy one computer that will do this. But it's way more interesting to see this case. I mean, for a course like this, I want you to see the case where I have a bunch of computers working together and some of the CPU cores are here and some of the CPU cores are there. Okay, the fact that you can multiply all these numbers by 100 and all you have to do is increase your budget by 100, there's nothing stopping you other than budget, and your code is ready for that is pretty cool. So what I don't want to do as a programmer is do it myself. If anyone has taken the distributed systems course, which is, I don't remember, for something or other, all of these things, or maybe some of these things come from even 201 or the operating systems course. They're so annoying, and they're even more annoying when they're spread out across more than one computer. Let somebody else do it. So the Hadoop world describes a whole bunch of technologies broadly in the big data world. But the ones we care about, on our compute cluster, Yarn is keeping track of, well, resources. It's yet another resource negotiator. The resources in this context are like CPU cores and gigabytes of memory, or maybe GPUs or that kind of thing. But it's basically going to be, I want my code to run, please. And Yarn is going to be the one that says, okay, we're going to put you over there. You're going to get these CPU cores, and off you go. And then if I have more data than can be stored in one spot, I guess I need to store it in more than one spot. So some kind of distributed file system. You can do network storage. There's plenty of other ways to do distributed file storage in the modern world, but this is one from the Hadoop ecosystem. And it's basically like, I've got compute nodes that can do compute work, and they also have storage on them. They can store data on those disks. The thing you're actually going to interact with the most is Spark. Again, this is effectively a competitor for pandas, like a way to describe computation that you're going to do on data sets. But here, in a way where you can do it or it can be done in a distributed way. You can hand a Spark job to Yarn and say, hey, give me 100 CPU cores to do this on, spread out across a whole bunch of different computers, and it's ready for that. Again, it's a way for a programmer to express themselves in the same way Pandas is. I want to do this computation, and there's a loop there, and the data gets, in this case, sent over the network or whatever. Spark will get it done. Here, again, we have this, I guess, design goal that we have concurrency happening. So when we're on the cluster, Yarn will take our code, like our actual program, and then get it running in a bunch of different spots so all the pieces of work can get done. Instead of reading files off the disk, we'll read files off of this distributed data store. The story is not so different otherwise. But let's not even tell that story yet. Let's just use Spark to write code. There's nothing wrong with running Spark just on a computer. I guess one thing, Pandas is almost entirely single-threaded. So the fact that you bought 4, 8, 12, 16, whatever cores when you bought your computer, Pandas uses one of them. Spark will use all of them, so that's cool. Like, if nothing else, that's good. I want to use those CPU cores. Oh, geez, is that true? That sentence is probably not true. You probably have to pip install on the Cecil workstations as well. Fortunately, it's easy enough. You do that. I did it, well, okay, fine. I did this before lecture. It is possible to run Spark on Windows. You pip install it, and then you have to put some magic file in some magic directory, and then it will probably work. Even step 2 here. I think actually the 2 steps are, this is the actual step. This is how you actually install Spark in the modern world. If for some reason that doesn't work, you can download it, unpack it, and run it. Almost certainly you don't have to do this. What you need to do is run some Spark code. So, well, this is Spark code. Let's, what do I call it? First Spark.py, good name. I updated a little bit, and I'll talk about that. Compared to the slides. So there's a bunch of like, this is just going to be there. This is just every Spark code program is going to have some analog of that. This is the actual work getting done. I'm going to read a CSV file, or in this case, actually a collection of CSV files. What I've said in the slide is that the CSV file will have a header row, and that you should figure out what the columns are and what the types of the columns are from that. That will work. It's insane in Spark. So I've switched over here. This is on my demo here. I have no header rows in my CSV files, and I've just said there's a city that's a string named this, and an int named that, and a float named that, and I've just given an explicit collection of data types. The reason is, if you want to do this, Spark has to read the entire file to figure out what kind of data is in there, and then read it again to actually build your data set. And that takes a long time if you have a big data set, so you probably don't want to. And then I can run it. Again, let's do that and that. That'll do. What's it called for Spark.py? This is so there's a whole lot of debugging junk that comes with Spark. Don't be scared. It just is. What I get is this. So I've read my data here. I've created whatever data structure this is. I've done a data.show that gets me that output. I've successfully run a Spark program. Good start. So the cities.csv, again, on the slides, I have this header row. I'm not going to do that in my demo here. I don't actually have one file. I have 3 files. This is a little more typical, but the same data is on the slides. So I have 2 rows in one file. 2 is a pretty small number. But that's okay. Spark is happy to read a directory full of files for us and create a data frame. So it's not a pandas data frame. I know data frame has always been unambiguous up to this point in the course. Pandas data frames and Spark data frames are different things. They are different data types. You can convert between them with a whole lot of warnings about whether or not that's a good idea. But Spark data frames are the same idea. Rows and columns have names and types. But I want to do the work concurrently across a compute cluster. So just the kind of methods and the kind of ways I'll interact with it are going to be a little different. And sometimes they're different just because they're different. Different people have different ideas. But again, basic idea the same. I read a file. There's other ways to create them, just like there are with pandas data frames. But now I really have to do implicit operations. I cannot loop over all the rows because the rows are maybe spread out across a compute cluster and they don't exist in one place. There's nowhere to loop. I have to do the right thing. I want to get this far and I want to do this code. Just as we're finishing up here, I know I'm running out of time. Yeah, let's do that. Okay. So this is, again, it's spelled differently than in pandas, but this is, I want to keep only the cities with a small area, and I want to keep only those 2 columns. I want to now throw away this column. I don't want to select it. So, okay, filter and select. I know how to do that in pandas. I know it's different, but the same idea. And I can print a pandas data frame in a Spark data frame. I have to do a .show, but it's the same idea. And I have some confidence now that if this was billions of rows spread out across a compute cluster, that this would somehow work with a whole bunch of concurrency happening. And that's awesome. Okay, that's, well, it's a good spot to stop because I'm out of time. So I'll see you on Friday. I will pick this up next week. See you then.